Today's basically AI applied to phenotyping day. So yesterday, for those who were here, we learnt the AI toolkit. We went from the basics of how neural networks work all the way up to agentic AI. And so now it's time to see how those technologies and methods and algorithms get applied in reality in fields that are relevant to all of us in agriculture. So our first speaker this morning is Dan Smith from the APPN, and I'm going to turn it straight over to him and let him introduce you to phenotyping. Thanks, Dad.
Thanks, David. So good morning, everybody. So I'm Dan Smith. I'm a research fellow here at UQ, and I work with the Australian Plant Phenomics Network. And so we tend to collect the data that then gets used in some of these AI models that we'll be talking about today. And so I'm really just going to give you an introduction to phenotyping, what the activity is, and how we go about thinking about what's important with our phenotyping. Oh, thanks, Dave. Great. Awesome. Okay, so I work in a pretty multidisciplinary team. So I'm studied crop physiology, but we have agronomists in our team. We have computer scientists. We have software engineers, and we have mechatronics engineers as well. So phenomics is a really sort of multidisciplinary activity, and we need to bring a lot of things together to make it work. So what is phenotyping? So phenotype is a combination of genotype, an organism's genes, and its environment. And so just the environment in which it's grown. And so phenotyping is the activity of sort of measuring traits. And a trait can be anything. So it can be anything that an organism expresses as long as it's measurable. And so when we think about crop improvement and breeding, so we'll be talking about genetics tomorrow, phenotyping is often seen as like one of the bottlenecks in crop advancement. And so it's a really important activity. So we could think about things like plant structure, how well it captures light, how quickly it grows in response to light or rainfall, deep physiological traits, ultimately yield. So for plants, yield is a really important trait, and even stress response. So thinking about drought or pests and diseases. So doing the phenotyping is really the link between the genotype and how the plant is performing in the field. So it's really important for breeding, for agronomy, and also for climate resilience. And so it's something that we really want to think about a lot. And so if you look on the left here, we sort of have like traits that we're trying to measure. So things like flowering time, biomass, plant height. And then trying to measure those requires us to automate different platforms. So we have drones, we have tractors, we have gantries, we have all sorts of systems to do that. But the real aim of it is to make informed decisions. So thinking about the ideal organism for a particular environment, and trying to select that organism. So in order for phenomics to sort of come about, we had a lot of sort of advancements over the past probably 100 years that allowed us to get to the stage we're at the moment. So, you could think about like mechanization. We had like early computer vision. We had the advancement of computer sort of chip technologies, and then also things like GPS and robotics. So phenomics really requires all of these things to come together. And so sort of in the late 2000s, probably early 2010s, that's when phenomics started to really emerge. And it's really the combination of a lot of different technologies coming together. And so, yeah, we needed faster computers for it to happen. We needed more accurate GPS so we could really geo-reference what we're doing. And also consumer electronics. So things like consumer cameras and drones, they drove the price of these sensors and technologies down to make them more accessible for researchers. And now we have robots and mechatronics as well. So all of these things converging. So when we're thinking about phenomics, we have to think about the platform. So that's the thing that we put the sensor on. And so depending on the scale at which we're working, we might have a satellite if we're looking at a landscape scale. We might have a UAV or a fixed wing aircraft. And then if we're zooming in a little bit, then we might have gantries or robots on the ground. And that's when we're starting to look at a leaf level or an organ level. And then in like a controlled environment, we also have even more precise instruments on these different platforms. And so this gives you an idea of the scale at which we work. The next thing is the sensor. So the next talk this morning is by Davud, and he'll go into a bit more depth about the different sensors. But essentially, we have all of these different technologies available which tell us different things about what a plant is doing. And so, RGB cameras, what we visually see, allow us to apply some of these AI models that we'll talk about today. We have multispectral cameras, so they give us information about the underlying spectral reflectance of a plant. We have hyperspectral cameras, which give us a richer sort of spectral profile that we can pull more information out of. Then we can measure thermal signatures, so actually the temperature of a crop to perhaps get some idea about how much water they have access to. Then we have 3D sensors, so LiDARs and 3D scanners. We also have sort of photogrammetry, which gets to the same thing. So that gives us an idea about the structure and the morphology of a crop. And then we also have spectrometers. And so there's quite a range of these sensors that are available. And in order to do the phenotyping, we need to combine them with the platforms that we're trying to use. So a couple of sort of considerations when we're thinking about phenotyping. So scale is really important, and there's different types of scale. So we have spatial resolution. So if you think about like a satellite image, a pixel is going to cover 10 meters. But if you have the exact same sensor on a drone, then a pixel might be at the millimeter resolution. And so depending on the thing that you're wanting to measure, this spatial scale becomes really important. When we're thinking about crops and how they grow and their reaction to environmental sort of inputs, then we think about temporal scales. So how quickly we capture data, because then that allows us to see at a fine resolution or maybe a coarse resolution what the response is to the environment. And so the revisit time is really important as well. Then we also have spectral resolution. So the amount of information that we record across the electromagnetic sort of wavelengths gives us information that we might not be able to see. So if we think about like, near infrared or UV or X-ray, we have sensors that can measure these things. And depending on the thing that you're trying to accomplish, then you might need to think about the spectral resolution. So all of these have trade-offs. We have, the cost trade-off. And then we also have, just the ability of the platform to actually do the thing that we're wanting to do. So this is kind of like an overview of some of the considerations in phenotyping. Ultimately, okay, so if you talk to phenotyping people, we really love the automation and the computer vision side of things. And sometimes we forget that the actual objective of what we're doing is to try and get traits. And so the traits are really important. And so getting that data from the sensor and then processing it in a way, and that's where the AI algorithms and the machine learning and those things come into play. Turning those things into traits that can then be used to make decisions is the most important part of what we do. And so anything that we can measure digitally and it has biological relevance is a trait. So we have things like state variables, so something that we measure at a particular time. So this could be something like plant height at flowering. That's just a state of the crop at a particular time, or maybe like biomass. But then we also have dynamic traits. So these are things that are integrated over time, and they're really important when we think about how crops and plants interact with the environment. So things like how quickly they senesce or how efficiently they use light over their growth. So this is something to think about because this is the most important part of what we do with phenotyping. Okay, so enough from me. We're going to do a quick phenotyping challenge. So if everyone wants to scan the QR code, hopefully this works, you'll come up with a form. So there's going to be a page. Just someone confirm to me that it's working. So you should have a page and it'll have 5 input boxes. And I'm going to get you in the next sort of 20 seconds, I'm going to show 5 images of wheat heads, okay? So you'll see, I'll give you a quick example, right? So what I want you to do in the first box is give me your guess of how many wheat heads are in that picture. And you've only got 5 seconds, okay? So if you are struggling to come up with a decision, just go with your heart because, that's where it's at. So I'm going to do it 5 times and we're going to see how this goes, okay? So is everyone ready? Okay, ready, set, go. 1, 2, 3, 4, 5. Okay, stop. Was that enough time? Okay, next one. Imagine you're a field tech and you're in a breeding trial and you have to do this for 1,000 plots, okay? Ready, set, go. 1, 2, 3, 4, 5. Okay, stop. Okay, next one. 1, 2, 3, 4, 5. Okay, we're nearly there. Oh yeah, do you need more time to type? Is everyone up to? Okay, is everyone ready? We've got 2 more to go. I know it's hard work. 1, 2, 3, 4, 5. Okay, type in your answer, and then we got 1 more. Okay, ready, set, go. Well, that one's a hard one. Okay, and that's it. Okay, once you're done, press submit. Okay, so how did you feel about that activity? Yeah. I mean, okay. So think about a field worker or someone who's measuring these traits. These types of things are really important for breeding pipelines. And in Shona knows, like in a breeding program, you might have thousands of plots. And so you're doing this every day. You're doing it from 8 a.m. to 5 p.m. So by the time it gets to 4 p.m., it gets pretty error prone. You're just sleepy, you want to go to bed. So there's a lot of error, it's time consuming, and it's subjective. So every person has a different idea of it. So if we apply things like AI models, we can start to be more objective, but there's a lot of considerations to make with these types of things. And so if we apply a wheat head detection model, so this is a YOLO V12 model on the same images that we just counted, you can see that, it does a fairly good job. It has a R² of 0.95. There's a bit of error there, but it's pretty accurate. So now, hopefully this works. If we go to your results, just bear with me. Okay, so we've got 35 results. Yeah. That can work. Oh, that's the wrong one. I knew this would be the hardest part of today. There we go. There we go. I'm not very good at computers. The rest of the team's better. Oh, no, it didn't work. That's a shame. Okay, we've got 1 response here. Yeah, I think so. Yeah. Oh, there we go. There we go. Yeah. Beautiful. We're nearly there, everybody. Oh, yeah. There we go. Okay. So then if I share that one. Perfect. So everybody online can see this. Okay. So someone guessed 10,000 wheat. I mean, whoever you are, congratulations. It's a great number. So you're kind of ruined by activity because we have an R² of 0. So if you work in our breeding pipeline, you're fired. The idea of that was hopefully to show you that, manually counting these things is quite subjective and time consuming. And, hopefully you have a good statistician or someone with basic stat skills who can get rid of those outliers. But yeah, anyway, back to the activity. So I'll just go back to this. Oops. The one. Okay, so yes, time consuming, error prone, and yeah, we have methods that can do this quite well. So why is this important? So manually screening traits is very time consuming. It's costly and it's error prone in breeding pipelines, but also just in crop science in general. I think, manual phenotyping is a big bottleneck. And so if we have technologies that can enable us to sort of do things more efficiently and quicker, then that's a really important thing. Yeah, and if we're going to try and do this across environments and at large scale, then it becomes even more necessary. So yeah, high throughput and accuracy is really, really key. And I'd just say that nowadays, I think there's this phenotyping bottleneck that's probably switched from like phenotyping and collecting the data to interpreting that data. So making useful sort of information from all of the data that we're collecting. In APPN, I think we collected, 100 terabytes of data last year. And so that's a huge amount of information. But if I were to just hand that on a hard drive to somebody, they're not really going to find that particularly useful. So we have to synthesize meaningful traits from this data. So that's where sort of integrated organizations for phenotyping come in. So there's a lot more of this happening nowadays. So the APPN is one of those. So where the Australian Plant Phenomics Network, let me get rid of that. And so we cover, I think it's 8 organizations across Australia. So UQ is the northernmost organization, but then there's basically organizations within the APPN across the country. And so we all have the same infrastructure, and we're really aiming to follow the same methodologies with that infrastructure to allow people to do research across environments. And so that's where you sort of get to the stage where you can collect really high quality phenotyping data sets that can be then used as inputs into some of these AI models and making some of these really big decisions. And so this is really important. And so UQ, we've basically got the project till 2027, and we'll be extending after that. And we've got quite a bit of sort of money to fund infrastructure that's important for plant research. So like I talked about before, we also work at various scales. So we work out in the field. So we have a mobile phenotyping unit where we can go to your field and we can collect data, and then we can either calculate traits out of the box, sort of things that are easier to calculate, but then we can also come up with a protocol and design sort of methodologies to help you answer your specific question as well. And so that's really important. Then we work in also Gatton. So we have a controlled field phenotyping unit where we can, this thing called the Cravo allows us to control the environment in which the plants are grown. And so we can close the roof and we can eliminate rainfall, and then we can phenotype in that environment so that we can measure how plants respond to drought and heat stress. And then in our glass houses as well, there's no gantry there yet, but we will be putting in an automated system that can measure in really high detail things like hyperspectral reflection and also photosynthesis and 3D models. And then if you go to the Plant Futures facility here in St. Lucia, we also have infrastructure in there. So we're really working across those different scales to try and measure these types of information. So why do we go to all of this effort? We really are developing sort of data sets that provide information to researchers who can use that to make decisions. We want to have deeper integration of AI into breeding pipelines. And it's also about removing the bottlenecks so that we can really operate at scale. The whole idea of this is about building more resilient crops that are adapted to changing environments. And finally, I just thought I'd add this. So I applied the global wheat head model to this image. If anyone takes a look at it, they'll notice it's barley. So, it's always important to have domain expertise because, it looks like it's working, but if you sent the cameraman to the wrong paddock, it's not much use. So, we always need to think about having expertise and people who really know what they're talking about in the field. So, yep, that's it from me. Thanks very much.
Thanks, Daniel. We have time for questions. So if anyone in the room have anything to ask?
Thank you. I just have a technical question. You mentioned about the heat stress in the glass house. I was wondering, how do you control the temperature? Is just by closing the shelving, and do you have any a heating source inside of the glass house things?
For that device, it's a passive sort of heating. So you literally just close the roof up and then you close the sides and then you have sort of a natural heating effect. But obviously you'd need to modulate that because I think if you close it in summer. We closed it in last year and it got up to about 50 degrees or so. So you'd just kill the plants. So you'd probably treat it as like, you know, like a thermostat. So you'd open and close it to get the temperature up to a certain level. And then, yeah.
Hey, are you guys using any really novel sensors, or is there anything else that you're beginning to test, or is there anything like that?
Yeah. So probably our most novel sensor, I guess, would be like our SWIR hyperspectral sensor. So that measures from 400 nanometers to 2500 nanometers, and it's a line scanner. So you attach it to a drone, and basically that gives you really rich hyperspectral imagery that's not very common. So the APPN, every field node purchased this sensor. It's worth $500,000, but that allows you to measure traits that you can't really measure otherwise. So things like water content and protein content could be estimated. So that's kind of novel. And then I'd say also the way that you use the sensor, there's novel ways of doing that as well. So Chris James in the room, he did his PhD with Scott Chapman, who's the director of APPN, and he's come up with some really novel ways of just using consumer drones to take really, really high resolution 3D models. And so that's a really interesting application. You could probably come and talk to us about that afterwards if you wanted to. Yeah.
Thank you, David. My question is, what is the acceptable precision, or how far have you already reached? Because most of the time after you do any of these things, you just validate, and then what is your acceptable kind of accuracy for this kind of?
Yeah, that's a great question. And I think it depends on who you're talking to. So you talk to the computer vision experts, they always want to have the most precise, precision possible. But then you might talk to someone from a more practical perspective who just wants to identify differences between treatments. And so those are two very different things. And trying to define what the acceptable level of precision is always like it's a moving target almost, because everyone's idea of that is a bit different. But basically, you need to be able to identify differences between treatments. So that might not mean having perfect precision. Yeah.
Just mentioned is it SWIR?
Yeah.
So you said that's drone code. Can that phenotype individual plants across that spectrum? Is it plant by plant?
Yeah, so you can fly it really low and then you can get higher resolution sort of data, so you can see individual plants. So your pixel size, with that sensor, it's not really, really high resolution. It might be 1 centimeter per pixel. And so you can still measure at a plant scale, but most of it would be sort of at a plot scale more likely. So yeah. Do we have any online?
All right, so I think we'll wrap that up unless there are any other questions. Nope. So thanks, Dan. Thank you very much.